right, I'll start the recording. Now, just in case you have not checked the email, for all those people in section GH, there is no lab tonight. The reason is the GH lab TA, Gabrielle Legendre, had exposure to COVID over the weekend. And so she has to quarantine herself and wait for the test results to come back. As a result, she cannot be present tonight in the lab because there is supposed to be experiment number 4 tonight. The lab supervisor has agreed to defer the setup. Namely, he was going to, for this week is experiment 4, so after Wednesday he would then take down the setup. But he has agreed to defer taking it down so that section GH, you will have your lab experiment next week. All right? So just in case you did not receive or you did not check your email, it is now the decision by the department with the lab supervisor's agreement. The other thing is, for the Blackboard exam, the grader also has apparently been sick. And so he says he has been recovering, and he said that he would have it all done by today, but I have not seen it. But anyway, this COVID exposure can cause many issues. But my decision, which I'm going to now announce, is that how shall I put it? There's an option. The option is that if you did well on test 1, because after all, even though not everybody was live in room MR3 on October 6th, yet Blackboard says everybody took the exam. And since I have no way of knowing on October 6th who were the ones that actually showed up, I mean, I did notice some names, but I do not have a record of it. There's no way to say only those who were present will have the test, the rest are cancelled. So in view of that, I now have developed an option. Option 1, since I have no way of knowing, if you did well on test 1 and you still want to keep it, when you know the raw score, what the average score is, and you say you did well, then you get to keep test 1. Then you have 3 tests for the semester, and then the final, and the homework, and now I will include the lab report. So that homework is 10%, lab report is 10%. Final count as 40%, and the midterms will count as, what is it now? I have to add 20, 40, so will count as 40%. All right. If you did well on test 1, you now have 1/3 of 40, so 13.3%, and test 2 and test 3. For those who opt out because they didn't do that well, then test 1 is not counted, and it will be only test 2 and test 3, and each one would count as 20%. But then you won't have much chance for recovery. If you, let's say, second test you didn't do that well, you don't have that much chance to recover, but that's your choice, right? And that will then be the options available. For those who want to choose to consider test one as being counted, you have to email me so that I have a record that you have requested it. Otherwise, it will not be counted, and you will only be counted on test 2 and test 3. Is that clear? Am I confusing everybody with my... I have struggled with this for quite a while, you know. Is it clear now? Yeah. So you, for the moment, you already have your own score. Somebody had a question. I forgot. I cannot see. It was so fast. Any questions to clarify this issue? Oh, what was the average score? Right now, the average score is, 100 out of 150, something like that. Let me see. I should have, wait, just 1 second. Yeah, right now it's 107 or something like that, 107. But the grader has to kind of go over and fine tune it a little. So I don't know, but it would be something like around there. Okay. And then you know if you did well. I mean, you don't have to have this option right away. I'm not saying within 35 minutes you have to send in your option. Let the grader with get over his sickness and he's now able to go through it all. At some point, I will then tell you what is the... So you don't have to email me now, but if let's say you did very well, you got the 180 out of... No, not 180. You got the 140 out of 150. Then you say, I know I'm going to do so well. I want it in right now. That's okay. But you don't have to... It's not like casting a ballot. And once you have cast the ballot, you cannot change the ballot. Well, there's a deadline for casting the ballot, okay? So you wait until this whole situation is clarified and you know your own score, and I will tell you what is the average, and then you decide, all right? Okay, is that clear now? And the overall midterms count as 40%, final as 40%, and the homework is 10%, and the lab count is 10%. And somebody else had a question. I didn't catch the... All right. What was the question? All right. Now, we want to sort of like complete this chapter, especially since the experiment on induction is towards the end of this chapter. And this entire chapter is on electromagnetic induction. And I'm not particularly happy with the way the book handles it all, but there are two ways to look at this electromagnetic induction. One is by what you call motional EMF, not emotional, but motional EMF, which really arose from what I would call the Lorentz force. How is the lab grade determined? Well, you better be showing up in the lab, and you better hand in reports that show that you actually have spent time and work on it. But pass, fail, I guess since it will count as 10%, maybe if the lab report says that you, according to whatever is the way they grade it, you got 8, 9 out of 10, you know, whatever. I mean, I will leave it to the lab TAs to show me. All right. I have no control over that, but it is the lab TAs. And I trust in the lab TAs because the department has used the TAs before. It's not that this is a new TA. And what was it now? What was the comment? All right. Anyway, well, somebody suggested if you pass, you get 10. If you fail, you get 0. That's a little bit on the drastic side. So anyway, I'm trying to be, fair. I'm trying to be accommodating, but up to a certain point. Okay. Yes, you had to pass anyway. If let's say you didn't show up for the last, 4, then you will have to make up for the 4. It used to be that if you did not show up for any lab, you have to make up at the end of the semester. They'll have a makeup date. But today, given the pandemic, I'm not sure the department can enforce that. So it's a little bit still evolving. It still works like that. I don't know. I have to check with the department, with the lab supervisor, whether there will be a date towards the end of the semester for rescheduling labs. All right. It gets very complicated because you have different labs for 203, 204, 207, 208. Okay. All right. Now let me come back to this whole subject of electromagnetic induction because I want to clarify certain things. When you have a magnetic field passing me by because somebody put a magnet near me and I have a charge, if I have no motion, if my velocity is 0, there's no force on me. But if I am sort of like in a conductor so that I am free to move, then of course I have a certain V. And then Lorentz force says that F is Q V cross B. It's one of the slides, you have it. And when you have it that way, you will now know that when I have a wire and it is now, let's say, moving in a magnetic field. If I have a magnetic field and I have a wire and I'm moving, then all the charges in the conductor, they are free to move, right? So they will move in the direction of the motion V that I have moved. I have caused this wire to move. So if I have caused this wire to move, all the charges in the conductor, they are now moving with a velocity V, which I am imposing because I am pushing this guy, right? And it is now in an external magnetic field. Then Lorentz force says, as a result, my charges now will have a motion inside my wire. You see what I'm saying? Here I am, I'm a whole column, and this is my wire. So there are all the charges in here, right? And now I am moving this. So because I'm moving this, all the charges will have a motion V in this direction of V. But now there's a magnetic field into the board, into wherever you're looking at the screen. So V cross B then says that all my charges that are free to move will now move upward. This is what they call motional EMF, that there's now an electromotive, unfortunately they call it force, EMF. But actually it is the electric potential because you take the electromotive force divided by the charge of that carrier. So there is a motional EMF, and the motional EMF is in the direction of V, whatever's the direction of your pushing me, cross B, and that now is the motional EMF. And the EMF that is induced depends on the length of your wire. So there is now a higher potential on this side versus the potential on that side. So that is motional EMF. All right. But now, for later part of the chapter, it is our friend Faraday who introduced this thing called Faraday's law, which looks at it in a slightly different way, but it's really the same underlying phenomenon, but looks at it from the point of view of magnetic flux. And then say that, oh, if you have a loop, whatever is the loop, and you now have magnetic field coming in. So I have the, let's say this is my loop. I don't have a wire loop, but anyway, I have a loop. And now you send a magnetic field coming through me because you put a magnet through. And now as you push the magnet through, you are increasing the magnetic flux through my loop. And Faraday says the EMF that is induced due to this is proportional to the rate of change of the magnetic flux. Because if you didn't push the magnet and my coil is here standing still, then nobody's moving. Then there is no change in the magnetic flux, the magnetic field, poking my area of my coil. There is no change in magnetic flux, therefore no induced electromagnetic EMF. That is Faraday's law. It is equal to the rate of change, and there's a very curious minus sign, which Lenz's law explained. So Faraday's law says the induced EMF is negative, minus sign, N, meaning the number of turns of your coil, because if you have one coil, then the induced EMF is such. But if you have 10,000 coils, then of course the induced EMF is a lot more, because they have a lot more of those charges that are now influenced by your change in the magnetic flux. So the two ways of describing it, one is motional EMF, the other one is Faraday's law, which is rate of change of magnetic flux. Both will give you the same answer if you are careful. All right, and we will come to a slide where I will then say Wiley Plus, whoever did that slide should have a slap on his face or her face or whoever's the face. But anyway, we'll come back to this. So now that we have Faraday in front of us, I just want to remind everybody, Faraday is one who was not good with trigonometry, and certainly was limited in algebra, but he's a good with his hands. And he did a lot of experiment and studied the whole field of electromagnetic induction. And his name is now famous because he published the papers. He published the results in the journal of that day, which is the Royal Society. And he is a chemist, and he discovered benzene, Bunsen burner. We use it all the time, and so on. But anyway, just to remind you that, and also notice this is 1791, because today we will be talking about inductance, which is an application of induction. And the name is Joseph Henry, and he is American scientist. Faraday is in England, whereas Joseph Henry is American, and I want to spend a little time on him. And he is also around 17, he was born 1797. And he also did a lot of work. But the difference between Faraday and Joseph Henry is Joseph Henry was like Isaac Newton. He did not publish. He just did the work and then he says, here, this you can now work with it. It works. Here, this now works. But he did not publish it right away, unlike Faraday. And so all the scientists around the world give Faraday the honor, although for inductance, the unit of inductance is named after Henry. So we will come to that. So, as I was saying, the EMF induced, the language that Faraday used is to say that it is the rate of change of the magnetic flux. And if you have a coil consisting of 20 turns with an area of such and such magnetic field that is perpendicular to the surface, and if initially it was 0.05 Tesla and later it was increased to 0.06, then you can say what happened. And now, one way that the magnetic field can increase is by you're bringing your magnet closer and closer and closer and closer, right? So that is where there is a rate of change of the magnetic flux. And the magnetic flux is, well, cosine phi just has to do with the angle relative between your face of this coil and the magnetic field. And if you just take it to be zero, namely it is perpendicular, then the magnetic flux is magnetic B, field B, times the area of your coil, and the difference between the initial and the final. And if you work out what is the final, it is 0.06, initial is 0.05, there's a minus sign. This then says that there is a EMF. And I don't like the notation that the book has, so I had to change it to curly EMF, all right? Any questions so far? I'm trying to familiarize you with Faraday's law. Any questions? All right. Because with inductance, this is the language that is the best for inductance. So for the language that they use for inductance. Okay, an induction stove. I already showed you last time that you can say, hey, I have, I don't know how much it costs to get an induction stove. I'm not in the market for it, but you have seen people with a fancy induction stove where this thing starts boiling, and yet this one, the board doesn't feel hot, because if the whole board is hot, you are standing there and you put your other spoons and etc. on it, you will say, ooh, it's too hot. But no, this thing does not get hot, and yet there's no fire. It's not a Bunsen burner. This thing is boiling, and it is all because what's underneath. What's underneath is that there is a a motor, a generator, and it is now generating magnetic field, changing magnetic field. And now this changing magnetic field is going to induce some current on this pot, the frying pan. The frying pan is made of, I don't know, some copper or something. And then because this at the bottom is now rapidly changing, this now produces many of these currents. And these are the eddy currents. And the currents now cause friction of your things inside the frying pan, and they heat up. And that is the secret. That is how the engineers have used the law of induction to actually now use it for our everyday purpose. Okay? So we leave it to the engineers. I mean, the engineers, they have to go through, graduate school in order to design better and better stoves. We want to now sort of understand why is there a minus sign, and understand this very cute principle called Lenz's law. Because when you induce something, you say, gee, how do I know which way it should go? And most of the time, if you're not careful, you get a minus sign wrong. But Lenz's law says the way you think about it is that the induced EMF resulting from a changing magnetic flux. You see, so this is the language of magnetic flux. It's much easier to pose it that way. The changing of the magnetic flux, it has a polarity, and the induced magnetic field is so as to oppose any change. Meaning, if originally I had a flux of, I think the unit for that is Weber. If I have, so much flux coming in through my coil, if initially I had this much, but then you, for some reason, don't like me, you move your magnet further and further away. Yeah, I don't know, because I guess you say it is now 6 o'clock and I want to have my dinner. Bye-bye, you bring your magnet away. If now you are decreasing my magnetic flux, okay? You are decreasing my magnetic flux. Therefore, there's a change in the magnetic flux. There's a certain rate of change in magnetic flux. And now Lenz's law says the induced flux, there will now be an induced current to produce an induced magnetic flux, is to make up, to oppose the change. If you are decreasing my magnetic field, I will now have a current so as to build back, oppose the change. You got it now? The current, my current will now flow in such a way as to now compensate, to oppose. So if you are decreasing my magnetic flux, my induced current that flows will make up for it. If, on the other hand, you really love me, you really want to come closer and closer and closer and closer to me, you bring your magnet closer and closer and closer to me, you are increasing the magnetic flux. Then the current that is induced will say, no, please, no, I don't like your smell. What you do is you will now induce a current to oppose it. So if the field is coming this way, you will now go the other way. Let me see. You want to go this way. You want to go this way so that the magnetic field opposes your increasing magnetic field. And that is this Lenz's law. Are you okay with this concept? Yeah, we will see a particular example of it soon. So I just want to first sort of build this concept that the Lenz's law is a very nice, neat way to put this thing about induced EMF. And if you now are increasing the magnetic flux, because you bring the magnet closer and closer to me, you're increasing the magnetic flux, then the current that is induced, the induced EMF will cause a current. The induced current that will flow will be such as to produce a magnetic field. The induced magnetic field is to oppose this change. So you're building it up. I will now have a induced magnetic field that opposes it to bring it back to the original. That is Lenz's law, and that is the origin of the minus sign. So the strategy is determine whether the magnetic flux that penetrates the coil is increasing or decreasing. Find what direction of the induced magnetic field must be so that it opposes the change, and then you will know the current, the so-called right-hand rule number 2, to determine the direction of the induced current. Okay, which is this. And now here I have the conceptual example 8. And here, Wiley Plus, whoever produced this slide, has a little issue with that. This is the coil that I have. And this is my magnet. And the original picture, if I don't know, this is from the book. So if you go to it, in the original book, they have the arrow this way, meaning that the magnet is coming towards the coil. But I correct it and say, no, what they show down here, the induced current, is for this case where the magnet is going away. You know why? Because if the induced current is this way, the current is flowing this way, then the induced magnetic field is in this direction. But if the induced magnetic field is in this direction, it's because my magnet is moving away. Can you visualize it yourself? In live, I can perhaps show you, but now I can wave my arm and you may not sort of see it. Are you able to see this now? With the current flowing this way, behind is up and up above is down. Now, if the current is indeed rising at the back, then the induced magnetic field is what they show, right? The current, the way induced current, if the induced current flows this way, indeed they are correct here. For this diagram, they are correct because the induced current is flowing up, so the magnetic field is going this way. But now, for the Lenz's law, for the induced magnetic flux field to be going into the coil, it must be because you are pulling your magnet away. Because you are pulling the magnet away, the magnetic field in my coil is now less and less. The induced current will say, I got to help, I got to help, I got to now build up. And so the induced current will flow the way they have it. That is for the magnet going away. I changed their sentence because they were saying, but this actually is moving away. This particular diagram applies for this magnet moving away. Are you following this? I mean, the concept is not difficult. It's just that you have to know how to use your, your thumb and the right hand rule. The way I use the thumb is, if my thumb is in the direction of the current, then my fingers wrap around the thumb in the direction of the magnetic field. So if this is the current that is induced, then this current in the coil now produces induced magnetic field, which is in this direction. And this means that I am making up for the fact that you are pulling your magnet away, because originally I had so many Teslas, but now you're pulling it further away. It is now less number of Teslas because the magnetic field strength decreases with distance away. All right. And so that's why my induced current flows. So this is the slide that they messed up. Whoever is the Wiley Plus guy doing it. So I downloaded another picture from the internet, which shows when you are approaching and when you are pulling it away, what's the induced magnetic field. And just you can practice with it. The way this one has it, it is going in and coming out in this direction, right? Going in, I mean the current is going in and coming out. And so if it is coming out, then the induced magnetic field is downward. You see it? If I look at this wire down here, it is above the board, right? And if the current is flowing with the direction of the current, then the magnetic field is downward inside. The induced magnetic field is downward. Why? Because you are coming closer and closer and closer to me. You are increasing the magnetic flux, but now I have to oppose your increase, so that's why my current has to flow in this direction. In this other way, you're pulling the magnet away. You're pulling the magnet away, so therefore you're decreasing the flux through my coil. And so my current now has to flow, above the board. It is flowing to the right. And so I got to now make up for it. So the induced magnetic field is upward to make up for the decrease. All right. Can you kind of try it out yourself at home with your hand, so on? Okay. All right. Now, this is a very tricky question until you realize it is basically Faraday's law, making use of Faraday's law. So here it says there is a region where you have a constant magnetic field, because in your lab you have a big magnet, and it has a north pole, south pole, and your magnetic field is over here, right? So there's a constant magnetic field directed into the page in this shaded region. The field is zero outside the shaded region. And now you have a copper ring. It is sliding through the region. And so you can ask several questions. First, while it is sliding out here, is there an induced current? I need some answers here. Don't be shy. You're not going to be graded on your response. There is no induced current. Why? Because there's no magnetic flux. It can be moving, let's say this is 10 miles away and it is coming. 10 miles, 8 miles, 7 miles, 6 miles, doesn't matter. And whether it's moving very fast or slow, doesn't matter. There is no magnetic flux. So neither increasing or decreasing, so no induced current, right? But now, when it is now entering, this area, is there an induced current? Just one yes, or is this two yeses, or huh? Right? Why? Because the magnetic flux through this ring is increasing, yes? And now if the magnetic flux through this ring is increasing, what does Faraday's law tell you? Or what does what does Faraday's law tell you? It says it depends on the number of turns in this ring, right? Your coil, whether it has 10 turns or 1 turn, doesn't matter, but it is negative of the rate of change of your magnetic flux. So here is where your velocity of your ring comes in, right? You can say Oh, it depends on how fast it comes in. If it comes in slowly, or the magnetic flux changes slowly. But if it is coming very fast at 75 miles per hour into my region, ooh, then the magnetic flux is changing very fast. Then the induced current is big. All right? Just conceptually, is that clear? Yeah. But now, once it has entered, it is now in the region where there is a magnetic field, therefore there is a magnetic flux. Is there now an induced current? Yes or no? Is there now an induced current? Yes, yes, yes. No, no, no. Is the magnetic flux changing? The shape of my coil didn't change, you know? Huh? The shape of my coil didn't change. My area didn't change. My magnetic field didn't change. So whatever's the speed with which I am zooming through this tunnel, there is no induced current. Are you following this? Because the shape of my coil did not change. And the magnetic field is the same here, 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 all over. Therefore, there is no induced current. All right? You see now? But now, when you're coming out, is there an induced current in the coil? Yeah. Why? Because now my magnetic flux, I was enjoying the magnetic flux. The magnetic flux was, so many Webers, Tesla meter squared. I was enjoying the magnetic flux, right? And then suddenly, because I'm emerging from this tunnel, I'm emerging from this area where there's a constant magnetic field, then my magnetic flux is decreasing. So now, whatever is the direction of the current induced is the opposite direction in order to make up for it. All right, so that is the Faraday's law. But then once you are really out, sorry, bye-bye, nothing to make up. All is lost, is zero. And therefore, delta phi, delta t is zero because phi was zero. And it will now be forever. I mean, don't mean forever, but all through the rest of my journey, there is no change in the magnetic flux. Therefore, no more current flowing inside my coil, induced current. All right, is this clear? This is a very good conceptual example. I mean, maybe somewhere there's a question which says, you know, the radius, you know, the diameter, you know, the magnetic field, and so on, and you know the rate at which you're moving. You can therefore figure out what is the induced, EMF, and therefore what's the current, because you know the resistance of this coil. But anyway, conceptually, this is the thing that we need to grasp. Okay. All right. Any questions about this? It says, for each of the 5 positions, determine whether induced current exists, and if so, find its direction. Well, in fact, here you can also figure out the direction. You are now, suddenly you find that magnetic field is building up. So which way should the current be? Should the current be clockwise or counterclockwise over here? Now we need to again take a little time to do with your hand, right? You are now having magnetic flux all of a sudden into the board. It's now increasing. You must now have an induced current that now has a magnetic field coming out of the board. So which way is the current? No, in the induced current in this coil. I didn't see the chat. Which way? Clockwise or counterclockwise? Counterclockwise. Very good. Because if it is counterclockwise, the magnetic field induced by this wire, the induced current, would then be coming out of the board, and that is to make up for the fact that originally it was zero, now you're building up, I want to oppose you. It's like friction, I want to oppose you. And over here, instead of counterclockwise now, it would be clockwise. Why? Because I'm losing magnetic field, so therefore I want to now have the current build up because I'm losing the magnetic field into the board. So I need to make up for it, and the current must flow in the direction such that the induced magnetic field is into the board. So it would be a clockwise. And you also notice that the counterclockwise and the clockwise flow is not permanent. It's just during the time of change. Then it stops. And then during the time of change, it goes the other way. That's why there's a lot of fun the engineers have, electrical engineers, and there's all these companies that are in fact involved in this, is where you have this tick-tock, where you have this alternating current, where you have things that go back and forth and do things that you would like it to do, right? This is all making use of this Faraday's induction, EMF. Here, this all is understood very clearly, concisely by this. Well, and then they say something about this. Now, I wouldn't even want to try to figure it all out because I say it's for engineers. You will not be asked on the blackboard. But it is nice that the engineers, ever since the 18th century, 19th century, 20th century, 21st century, all of these instruments, they are much, much more sophisticated than what we are able to understand. But it all comes from Faraday's law. And same thing with the, well, we'll leave it. Even for the mic, it's a something that involves. Okay. Now, we want to deal with a generator because we have that. Without the generator, we will not have the power, we will not have our light, we don't have our electricity. And the principle behind a generator is you have a magnet, and for a power company, the magnet is a big magnet, not the bar magnet that you play with, right? But you have a magnet with a magnetic field, and then you have a coil, because by now you can see you want to use Faraday's law, it should be a coil, and you now rotate this coil. Now, if you rotate this coil, there will then be a change in the magnetic flux through this coil, and you will therefore now induce an EMF, and this EMF will cause the current to flow. And if you have your lamp over here, you will then have this light burning. Okay, and so for the generator, it's easy to understand it in terms of Faraday's law. All right, and the flux is the perpendicular component of the magnetic field, normal to the surface area A, A being the area of this coil. So what the book explains it. Okay, wait, let me go back to here. And here it's easy to explain. It's easy to explain. Why? Because you are now turning the coil in the direction that the diagram shows. So what happens is, when it is in this position, the magnetic flux is less. But when you now turn it such that it becomes perpendicular to B, it becomes the maximum. So during this phase, while it is turning from not yet perpendicular to the perpendicular direction, the magnetic flux is increasing. All right, the magnetic flux is increasing, and then what it will be is that because the magnetic flux is increasing, the induced EMF would be negative, and the current that flows is, which way? I don't see it. The magnetic field, the flux through it is increasing. So what I would do is oppose it. That's why my current now will flow upward, because if my current is flowing upward, it will now introduce the induced magnetic field will be opposing the flux. You see it? Are you able to see this? I have this coil, and it is not exactly perpendicular. So because it's not exactly perpendicular, the flux through the coil is now increasing because you're turning to make it more and more perpendicular too. So as the magnetic flux is increasing, I want to oppose it. And to oppose it, I have to have my current flowing in this direction in order to oppose it. So I am good with Lenz's law to explain this minus sign. And then Faraday gives you the actual electromagnetic EMF. Okay, so this is how I would very quickly explain this generator. And then the other thing is, when it passes this perpendicular and goes beyond, then what happens? The coil is now turning sort of like from maximum flux is to decreasing flux. So as it is continuous in its turn, the flux is now decreasing, and then the Lenz's law says, hoo-hoo, I need to have induced current in order to build back. And therefore, when it is now on this side of it, the current is opposite direction. You see what happens? It now has to build back. So I got to now have it, the current flowing this way, so that it now compensates and builds back the flux. So this is using Faraday's law to explain the AC generator. This is an alternating current generator. The motor still goes. The motor is still going, whatever the same direction. It is not tick-tock, tick-tock. It is just going, right? And it is keep going. But the current that is induced, generated, is an AC current, because while it is in this phase of it, the current is flowing upward. But then when you go beyond this, the current is going downward. So it keeps going up and down and up and down and up and down. So this is an alternating current. All right. Are we comfortable with this? Are we comfortable with this? Okay. All right. But now the book does it a little bit more I consider clumsy, but I guess it depends on how you were brought up. You have. And so what they do is they say they want to look at the motional EMF. You remember at the beginning of the chapter, it was motional EMF. It was only in the later part of the chapter that it came to Faraday with the Faraday's law of in electromagnetic induction. So they say, hey, I want to write this as the velocity is really V cross B, the velocity with which this rod, right? Think of this rod. You remember? I have a rod moving in a given magnetic field. And when a rod is moving against this magnetic field, there is a motional EMF. And that motional EMF, that you trace its origin to the Lorentz force, which says that F is equal to Q V cross B, right? And so as it is now turning, this rod is now moving, and V cross B is V sine theta times B, and the potential difference that builds up has to do with the length of this rod. So this is the motional EMF. Well, this V is R omega. Why? Because this coil is turning with a certain angular velocity omega, and the radius is half of this width of the coil. All right. So the radius is half of the width of the coil, and the angular velocity with which the motor is running. The motor is running at 60 cycles per second. Right. So there is this velocity of this rod in this external magnetic field is now W over 2 omega. So you put it in, it's BL, is the length of the rod, now times W over 2, because the radius of this this thing turning around, the circular motion, you know, is W over 2 omega. So therefore, this is BLW over 2 omega sine theta. And theta, of course, is omega t, because you know it is turning at the angular velocity omega. Now, L times W is the area, right? So we are more sophisticated. We say, hey, you silly guy. I mean, maybe you don't call him silly guy, but you naive guy, you poor guy. This B times LW is really the flux, phi, okay? But anyway, we follow them because in this book, they go by their own, they go by motional EMF instead of using Faraday's law. And so we now say, the induced EMF in this AC motor is now BA, which is the flux, omega, the angular velocity, sine omega t. Now, that is their answer. Oh, wait. Now, there is a tricky thing. When I first saw this, and then I saw this, and I say, wait a minute. Why do I say wait a minute? Because there's a factor of half. Where did the factor of half? What happened to the factor of half? And then you have to say, wait a minute. There are two arms of this coil, you know, right? This is the rod. This is the other rod. On this side, this is the induced motional EMF. But on the other side, there's also motional EMF, and it is helping. It's, you know, one side's up, one side down. It is helping each other. So therefore, the total motional EMF is double. Are you following this? As I was, working with that slide, I kind of like saying, gee, I should be paid for this. They have all these little things that they didn't fully explain, or at least in the slides they didn't explain. I didn't go into the book and look at each sentence in the book. They probably in the book, if you read it carefully, verse by verse or sentence by sentence, they would have explained it. But on the slide, I say, how come there's a factor of 2 missing? Well, that's because you have 2 arms of this coil, and on this arm, the current has to flow upward in order to sort of oppose the increase in the magnetic flux. On the other side, it must also be opposing, but then because it's on the other side of it, it must be now downward. And when you have the 2 of them together, it becomes just this. Therefore, the net electromotive force is N, the number of coils, the flux, and omega sine omega t is really the rate of change of the flux of the area, because B perpendicular times A, it's B A cosine of the angle, and the rate of change is therefore omega sine omega t. So this then is did you follow where this comes from? The flux is B cosine of the angle times A, because it has to be the normal to it. And when you're not, then it is B cosine theta times A. But it is the rate of change. And, I don't know, you don't know calculus? If you take the rate of change of cosine is omega sine. So this is where this thing came from, omega sine. All right? And the minus signs take care of themselves, because rate of change of cosine is negative, and then with a minus sign becomes positive. So this then is the Faraday's law of electromagnetic induction, the induced EMF, which the book, the Wiley Plus people, derived by using this motional EMF, which takes a lot more work to figure it out. And the net result is that this is then the AC generator producing the electromagnetic, your current. And this omega is 2 pi f, and this f is the frequency of your motor. And you can then have, all right? Okay, any questions about this generator, electric AC generator? Okay, now let's go on. Yes, no, okay, let's go on. And now the book also then goes into more for engineers. You see, electromotive force is a very interesting subject, which is why all these companies, Siemens and so on, they really spend a lot of money in hiring engineers, because what happens is, even as you're producing the electricity, there is a counter torque, because there is an induced EMF for everything that you do. Everything that you do, you're turning. Well, even as you're turning, there is induced EMF against you. And so this is what they call counter torque. But now we are not going to go through it. I put down here for engineers. You are not electrical engineer, and I'm not electrical engineer. Let them handle all the tricky things, due to the fact that is a counter torque that counters your rotational motion, because you are trying to make it go at constant 60 cycles per second. But even doing so, there is in your machinery, there is counter torque. So we won't deal with this. All right. let's call it the back EMF generated by electric motor. Leave it to the engineers. Okay, leave it to engineers. We won't do this. But we want to come to inductance because after all, your experiment is on inductance. Okay, and inductance is very important because transformer is also very important. And we live with transformers because, as I mentioned, I must have already mentioned it, the power company generates it at a very high voltage in order to reduce the current that comes out, in order to reduce the power loss due to the heat loss, I squared R. And in order to do that, they have to step up the voltage. The motor, the generator, generated it at a certain voltage, but now it's not high enough. They have to step it up, step it up, step it up to 675,000 volts. How do you do that? It is basically through mutual inductance. So it is a very important subject. It's important for our applications. The changing current in the primary coil. So now, what is a inductance? You have a primary coil. It didn't have any. All right, I didn't supply any current through this secondary coil. I only supplied my current, my generator, to this primary coil. But this primary coil, because I have a current through it, produces magnetic field. And this magnetic field penetrates the other side. When we have a transformer, you will see that there is a magnetic, ring. And on one end of it, you have your primary coil. And then on the other end of it is your secondary coil. So I have a primary coil where I have a generator connected to it, and it now flows. There is a primary current, I, and so there is a magnetic field produced by my current. Now, this, because I have a changing alternating current, so for one part of the cycle, the magnetic field is this way. Another part of the cycle, magnetic field is this way. Another part of the cycle, magnetic field is this way. So magnetic field is going back and forth because this current is going this way, that way, this way, that way, this way, that way. All right. And now, as a result, the guys over here will say, ooh, my flux going through me all of a sudden increases, all of a sudden decreases, all of a sudden increases, all of a sudden decreases. So there will be now an induced current. So this is what you call inductance. It's mutual because I could switch it to the other side. I could stop the AC generator here and I start over here. Well, it will induce the current, the current over there. It's mutual, right? So we call it the mutual inductance. And it is again based only very simply in terms of this, very elegantly in terms of this. Well, if I now have this and it induced, I would like to know what is the EMF that is due to mutual inductance, meaning what is the induced EMF here that is due to my changing current over there. All right, you see the formula? It says, I would like to know how much is the induced EMF on the secondary coil due to the fact that my primary coil current is changing. Of course, the primary coil is changing, therefore there is a magnetic field produced by the primary coil, and as a result, it causes this. But the engineers would like to just simply relate it by saying You tell me what is the rate of change of your primary current in your coil. You don't have to tell me the radius of it because we have arranged it so that the radius of the coil are the same. And so you let the engineers figure out what is the magnetic field due to a current, and you due to a change in current, you then know what is the magnetic field, and then you flux, and therefore you know what's the flux and the rate of change of flux. So all those factors having to do with what's the magnetic field strength due to a current I is all absorbed into this, which we call M. Are you following me? The concept? That the fact that there is a current in the coil, there is a magnetic field produced. And if you now change the current, the magnetic field that's produced will also change. And then this magnetic field is now flowing through here because my secondary coil is part of this setup. And so that flux, because we have the same radius, the same area, I now know what is the change in the magnetic flux over here. And therefore, I can now know what is M. Now, if this coil, the radius is different, then the magnetic flux coming through here may be different than this because this area is smaller. But the engineers will then include all of that into their design and say, oh, the M for this particular design, where this particular coil is tiny compared with this big one, then the M is a different number. And when they sell you this transformer, I mean, engineers, when they build these things, they will have already told you, yes, the mutual inductance for this particular setup that they have, for which they sell you for whatever cost the money is, then you just only need to use that number. You don't have to work it out yourself. But for Wiley Plus, maybe they will say, here, there will be some problems where they say, this one is of a certain radius, this one is of the same radius, and this is the current that is changing, what is the EMF that's produced, and you can work it out. But is the concept clear now? Is the concept clear? Is everybody asleep? All right. Okay. So, yeah, it makes sense. I mean, the actual numbers, you have to, search through the formulas. For the moment, let's just get the concept that this primary current going through this coil will produce a magnetic field. Therefore, there's a magnetic flux. And this magnetic field will now cause a flux going through this secondary coil. And because your primary current is changing with time, this magnetic flux through my secondary coil will change with time. And then Professor Michael Faraday already taught me that there will be an EMF. And that EMF is now called the secondary EMF, right? So, okay, so now this is called mutual inductance, and the unit, which is, this is unit volt, this is, of course, amp, and this is second, and the unit for mutual inductance is Henry. And so I'm always very curious, and I was so interested to find that this Joseph Henry is New Yorker, yes, born in Albany, New York. At the age of 13, became an apprentice watchmaker and silversmith. In other words, he's good with his hands. Yeah, he's a very curious guy. He's good with his hands. But his interest in science was sparked at the age of 16 by in those days, popular lectures on experimental philosophy. Of course, today it would be popular science. So he was interested at the age of 16, and in 1819, now how old was he? 1819. 22 years old, he entered the Albany Academy, which is a free academy. And do you know City College is a free academy of New York? But City College is not as old as Albany Academy. So, but anyway, he was not from a rich family. He was given free tuition at the free academy. And in 1826, by which time he was 29 years old, thereabouts, he was made a professor at Albany Academy. In other words, it's like CCNY. You were a graduate of CCNY, and then later you became famous, and CCNY says, please come back as a professor. Now, what he did, and that is very interesting, he was not a scientist like Michael Faraday, associated with the Royal Society. He was simply more interested in doing experiments. He's really an experimentalist, yeah? And he created one of the first machines, which is the earliest ancestor of DC motor. You notice we spend quite a time discussing AC motor because after all, you rotate and then you find, the current will now flip over, right? As you turn, current will flip over. But our friend Joseph Henry was very smart, and he actually flipped the magnet. I don't know the actual arrangement of it, but this apparatus that he invented allowed to Henry to have this self-inductance, which we will come to, and Michael Faraday also recognized this at about the same time, but Faraday published his result first, so he became officially recognized as the inventor or discoverer of self-inductance. But there are many historians that say that Joseph Henry should be. And indeed, in America, Joseph Henry is honored. Later on, he became Secretary General. He became president of what today is Princeton University, and so on. So he has lived to an age of 80, and I was interested to see that on the Wikipedia, they say that he is known for electromagnetic induction and inventor of the doorbell. I say, ooh, each time anybody presses the doorbell, ding dong, it is really Henry, yes, an electric relay. Anyway, I just wanted to. So now we come to self-inductance. If you have an AC generator and you now have a changing current in your coil, the very fact that your current is changing means that the magnetic field is changing, and then the very fact that your flux, therefore, through this coil is changing, it itself induces an induced EMF. You see now, it's self-inductance. Well, now we also, the engineers, will now say, okay, instead of dealing with the language of magnetic flux, we now again just deal with the changing, the rate at which the current through my coil is changing, and then absorb the magnitude of the magnetic field and then the area of this coil in this thing that we call L. So instead of writing E is minus N d delta phi delta t, we write it as minus L, the self-inductance, times delta I over delta t. All right. The fundamental law is the rate of change of magnetic flux. But for engineers, they like to discuss it or describe it in terms of rate of change of the current. So you now introduce this. This is called self-inductance, and the unit is again Henry. And now, this is the engineers, they have worked on it some more, and they find that the energy stored in an inductor is 1/2 Li squared. You're not going to be responsible for it. And the energy density inside this inductor, because it's all full of magnetic field, is B squared over 2 mu 0. Mu 0 is this permeability. This just so that you can know that in the inductor, you have stored energy in there, and the energy that you have stored in there is proportional to I squared, and it's the, if you want to do it in terms of the magnetic field, because the current I produces a magnetic field, so instead of writing it in terms of I, you can write it in terms of B, and then the energy density per unit volume is B squared over 2 mu 0. We won't directly use it, although later on, when we talk about electromagnetic waves, we will refer back to this. All right? We don't have to go into the mathematical details how to get this energy out of it, because you then have to get into the energy concept of what is the amount of work done. But I want to end with transformers. You remember I said a transformer is really a device for stepping up or stepping down the current or the voltage. On one side of this magnet, and this is what they call an iron core, you have a permanent magnet. Although these days, the electrical engineers, they can actually have magnets that are not from the mine, that they actually manufacture a magnet that is whatever shape you need for your application and of a certain strength, because they are able to supply the current to produce magnetic field. Anyway, so let's say that there is this magnet, a permanent magnet, let's say, for simplicity. And on one arm of it, you now have an AC generator. And this AC generator provides a primary current. And therefore, there is now a magnetic field that is now produced. And this magnetic field is now produced, whatever is your original iron core, you now have the added magnetic field. And this iron core directs the magnetic field through it, because that's the nature of the material that they use. If you have more magnetic field due to this AC generator, then the individual little magnets inside this magnetic material, or they will all be lined up, and they will now all be sort of pointing in this direction and going around the whole arm of this device. Well, therefore, what you have done is you have now been increasing the current, and because you have been increasing the current, you've been increasing the magnetic field inside this core, this what would you call this? You can call this a ring inside this gadget, right? Inside this gadget, you now have increased magnetic field strength, and this magnetic field strength will now pass through the secondary core, and this secondary core did not have a generator. However, this secondary coil will now have induced EMF, and so there will now be a current that can flow if you have a switch on. So you now would like to know, what is the resulting, let's say, potential on this side? And this is the one that you now use for whatever purpose you have. And this is called a transformer. Why? Because you will have induced, and the current that flows on this side will be different than the current that flows here, and the potential that you find on this side is different than the potential you have over here. The secondary EMF is now the number of coils on this arm of the transformer. That's the secondary. Using the Faraday's law is then the rate of change of the magnetic flux. And the primary EMF on this side is whatever is your magnetic flux that you produced times the number of coils on this side. So if you now say, what is the ratio? Because the magnetic flux is the same. Why? Because this gadget sort of focuses the magnetic field through it all, and this is all of the same size. Therefore, the magnetic area is the same, the magnetic field is the same, and the area is the same. And if you now say this one, the magnetic field is increasing, well, it's then the same magnetic field increasing on the other side. Therefore, the rate of change of flux through here is the same as the rate of change of flux through here, because the area is the same. The two arms have the same area. All right? And so you can therefore say, see, I now know whatever is the EMF on this side, the EMF on that side depends on the ratio of the secondary coil, the number of turns, versus your initial on this side, NP. So this is the transformer. I can step up or step down by having more and more coils, turns, versus my original one. And you can therefore now say that the voltage, if I want to step up the voltage, I have a lot more turns of the coil on this side. If I have a lot more turns of the coil on this side, then the voltage of this, the EMF now is much bigger. And if the EMF is bigger, when I now put the switch on, oh boy, the voltage that comes out is now maybe 100 times. Of course, for the power company, they step it up from, I don't know, let's say 200 something volts to 675,000 volts. That's a big number of steps, and they don't do it in one arm, they do it in steps. So in the substation, when it first comes into New York, there's a big substation, and then they step it down, and then they go to the next substation, they step it down, and so on, because to do this transformer in the industrial scale, it takes a lot more issues involved. All right. So this is the transformer equation. And now the other thing that a transformer does is that if you now want to know, I have a current. If I step, let's say I have a certain power. This is my generator, and it produces a certain power. And the power is so many megawatts. Now, remember from chapter, I forget now, is it 20 or something? Yeah, I think chapter 20. The power is the current times the voltage. Do you remember that? Do you remember that the power, huh? Was it from chapter 20? Was it chapter 20? Yeah, P equal to IV. Power is I times the current times the voltage. But now, if I now have this generator and it supplies this much power, that power must be the same power on this side. Because if not, my this gadget melted, or if not, my gadget, I don't know, something. Energy must be conserved, right? So if I have this much power, it's the same power now on the other side. But now you raise the voltage up. What if the power remains the same? What happened to the current? The current comes down. So if I want to know what is the current on the secondary coil versus the current in the primary coil, it's opposite to what is the voltage. If this voltage is big compared with this, right? If this voltage is big compared with this, then it says that my current now is, what is it? If this is big, so this is a number less than 1, then the current through this is now small. If I stepped up the voltage here, the current through here is small. And that's what the power company needs. The power company says, I spent such a lot of money designing this big hydro power generator, right? In Niagara Falls, I generated so many megawatts. I really did spend a lot of money and so on to generate this. But now I want to reduce the current. What do? I step up the voltage, and inside my generator plant, I step it up to 675,000 volts. Therefore, the current now is much less. And I arrange it more than this simple example. It's a very complicated, setup that they have. But then my current now is small, and it is having a small current that enables me to not lose that much power, because the power loss due to the thermal heat, due to the fact that the wire begins to be hot, is I squared times R. And if I'm able to make I small, then I'm able to make the power loss small. And this is the picture. The picture is one where you have your hydroelectric plant. It was at so many megawatts, I don't know. And then, well, this picture is an old picture. What is it, 240,000? If you look it up today, I think the high one is 675,000. At least I remember that number. And the reason is, if you're able to design a transformer at your plant that is able to raise it up to 675,000 volts, then the current that flows in this high voltage transmission line, the current that flows is smaller. And if the current is smaller, the power loss is I squared R. So the power loss is smaller. And then they choose the wire so that the resistance is also not that big, so that the loss, let's say I had, let's say 6 megawatts or 10 megawatts. By the time it comes down to New York City, I still have maybe 9.7 megawatts. You want it to be low transmission loss because you make money based upon the power you supply to New York City. So they step up the voltage to very high, then transmit it across, and then when they come to this end near the, well, not the house, but to the city, then what they have to do is to lower it. When they lower it, they have to have a transformer to step it down. A station will step it down from 675,000 to maybe 425,000, and then to 240,000, and then to 120,000, and so on. So they have to then have a sequence of substations. Like in Teaneck, we have a transformer substation that I don't know, steps it down to the one for our household. So power companies, they have to install all of that such that in the end, you will step it down to the household. And in America, they step it down to 110. But as I mentioned, I don't know, did I mention it? It must be earlier when we were doing in chapter 20. In Europe and elsewhere around the world, they, for economic reasons, step it down to 220 volts. They say, it's okay. They don't mind if you get an electric shock, although the likelihood is if you get an electric shock, you might be fatal. Whereas in America, electric shock is just a shock. But anyway, the rest of the world, they say it's okay to step down to 220. No need to spend that much more money to have another transformer. So in Europe, elsewhere is 220, but for us, we are 110. And this then is the picture for transformers. And I think that's it. So you are in time for well, not for for the section GH, you will not have the lab. You will have the lab next Monday. But for GH2 and GH3, you will have your lab experiment on induction. Any questions? Oh, homework 22. Is this 22 now? I get it all. It's up now, right? Can anybody check on it? Is homework 22 now up? Yeah. Oh, no? Well, I set it so that it should be up. So if you don't find it up, I guess. Okay, any questions? Have I gone too fast or too slow or? The whole chapter is on this issue of induction, EMF. And there is the motional EMF, which is like the slow poke way, whereas the Faraday's law of induction is the most sophisticated way. But in the end, they are the same. It's just that the language is more convenient. And then for the engineers, in the end, they don't want to deal with the rate of change of flux. They want to do it as rate of change of the current. Okay. Any other questions? If not, I will now. Okay, I will stop the recording. Now somebody said that you have a question.